thanking the organizers for the opportunity to be in Natal again, which is always very, very good. And I would like to say that there are some typos in my talk that I've been repeating over and over, and I couldn't find it because I cannot spell in any language, which shows that women does not necessarily have infinite memory. So it's an exercise for the audience to find it, okay? So today I want to talk to you about this work that I did with Adan Cabello, Marcelo Terra, and Leandro Olita. And some results that we have been working on in the search for a resource theory for contextuality. So contextuality is a feature that may arise in the statistics of joint measurements in a system that shows how these statistics deviate from what we expect using only a standard classical probability theory, okay? So we know that quantum systems may display contextuality, and this has a major role in foundations of quantum theory, but it has recently been shown that this contextuality thing has also important applications in random number generation and models of quantum computation. So besides its importance in foundations, we know now that contextuality is good for other purpose, practical purpose. And contextuality is related to the advantages of quantum systems over classical systems, okay? So every time we know that some feature is used as a resource for practical applications, we would like to develop a resource theory for this property. And these resource theories give us a mathematical framework to study this property as a resource. Okay, so resource theories, they are constructed basically with three ingredients. The first one is the set of objects, which are the entities that may or may not possess this resource, okay? And inside the set of objects, I have a set of free objects, which are the entities that have no resource. The second ingredient is the set of free operations, which are operations that map one object into another. And in some sense, when I have a resource, I think about this property as something expensive to generate in some sense. And I want to know what operations I can do for free without having to generate this resource without any cost in this sense of this resource. And this is where the non-contextual warnings come. And the third ingredient is quantifier that will give me a quantitative notion of how much resource a given object contains, okay? So it only makes sense to talk about quantifiers if I have a good notion of what my free operations are. And this will be clear in a few minutes, okay? Okay, so I'll first talk a little bit about objects. And I don't know how many of you are familiar with contextuality, so if you are not, please stop me at any moment. So here I am basically concerned with a set of measurements that I can implement in some physical system. Here I will imagine that I have a finite set with a finite set of possible outcomes for each measurement. And I'm interested in measurements of some of these measurements jointly. So I have a set of contexts that tells me which sets of measurements I can implement jointly. Okay? If I'm thinking about our quantum systems, these contexts contain only compatible measurements. But here I'm not concerned with quantum systems specifically, but this is a way of thinking. Always think of this context as containing compatible measurements. Okay, so to make everything I'm talking about here more clear, I will use this very, very simple example in which I have three measurements, A, B, and C, and two contexts. So I know that I can measure jointly A and B and C only. That's the only thing I have access to, okay? So I will imagine all of these as a box, okay? So the measurements are represented as input buttons. So in my example, I have 3 input buttons. And the outcomes will be output lights. I'm not very concerned with the outputs here today. So in my example, and the contexts are the rules for pressing buttons jointly. So in my example, the rules here is that I can press A and B, have some outcome, and I can press B and C. So this is the rule for my example. Okay. So I'm not concerned with the specific structure of the physical system. I'm only concerned with probabilities. So I'll describe my box by the probability distributions for each context. So if I press these two, I have a probability distribution for the output in this situation. And if I press these two buttons, I have a probability distribution in this. So this is what I call a behavior that will tell me the functioning of this box. So it's just a set of probability distributions, one for each context. Okay, so in my example, I have two probability distributions in a one for the first context and the other for the second context. Okay? So now I want to make some restrictions that are imposed because I'm considering a physical system. So the first one is that I want boxes with what we call non-disturbing behaviors. So what I want here is that if I have two contexts that overlap, the marginals computed for the intersection has to be the same whether I use this distribution or this other distribution. Okay? So in my example, I have two contexts, and the intersection of these two contexts has the measurement B. And I can compute the marginal for B using this distribution summing over A, or this distribution summing over C. And the answer has to be the same. Okay? Because in some sense, I'm thinking here that B is the same measurement, so it has to be the same statistics, whether I measure it with A or with C. Okay? So this will be the set of objects for me. Boxes that have non-disturbing behaviors. Okay? And the free objects for me would be the boxes with what we call non-contextual behaviors. So these boxes are the boxes such that there is a global probability distribution, which is a probability distribution for all measurements at the same time, which would correspond to a hypothetical situation with which I could press all buttons at the same time, such that the probability for each context is obtained as a marginal from this one. So in our example, this corresponds to the existence of this probability distribution, this global probability distribution for the three measurements, such that the probability for context AB is obtained with this marginal over C, and for BC with this marginal over A. Okay? So I will not enter into the details here, but this is related to the possibility of explaining the behavior of this box using classical probability theory. So that's why we can also call these boxes classical. Okay? So these are the classical or non-contextual boxes. They are the free objects, and I mean the resource are the non-classical boxes in this sense. Okay? So this is the set of objects, and this is the set of free objects. Questions so far? Okay. So now I'll talk a bit about the free operations for the resource theory of contextuality, which the objects I consider are these boxes. And this has appeared in this really nice paper here. And the idea is to define a class of operations that transform one box into a box, maybe in a different scenario, in such a way that if the initial box is non-contextual, the final box is also non-contextual. So are the operations that will not generate contextuality out of nothing. Okay? And the idea is the following. My target box is this one, so this is the initial box. And basically what we do is use here a non-contextual box as pre-processing. So before entering the inputs in the second box, I will pre-process the information here. And after obtaining the outputs in the second box, I'll have a post-processing box that will post-process the outputs of the second box. And this looks quite simple. But there is something that we would like to have to be as general as possible, and what we would like to have is the post-processing to depend on the pre-processing. So I would like to have like this arrow here, okay? And with this definition, I'll have now a final box with this set of inputs and this set of outputs. And the probability for the final box is computed in a very simple way, just taking the products of the all possible paths that I can start with a context here and obtain a final answer here, which will give me something like this. So this is the probability for the first box, this is the probability for the second box, and this is the probability for the third box, and I'm summing over all possible paths that I can have. And here you see that the third box, the probability in the third box will depend on what happens in the first box. Okay? So this looks quite simple, but there is one problem here, that is that I don't want to create contextuality. So one condition that I need is that the first and the third box be non-contextual, of course. But this dependence here, if I don't take care of what it can be, can also create contextuality. So the thing that took us longer to figure out is what we need to impose on this thing here in order not to create contextuality with the dependence of the post-processing with the pre-processing. Well, the answer is the same. Like, A depends on X. Yes, not directly. And because here the choice of the inputs in the third box depends on the output of the second box, but just this. Maybe if it depends on X directly, we will have something more general, but I have to think. Okay, so to explain to you why it was difficult to figure out how this dependence had to be, let's first see what happens in a Bell scenario, because here is easy to solve the problem. In a Bell scenario, a box is split into halves. One is separated from the other, and there is a wall in the middle. And I know that what happens in one side cannot influence the other side. So when I talk about these wirings for Bell scenarios, I have the pre-processing also divided in two parts and the post-processing also divided in two parts. And the rule here is very clear. I know that what happens in this side cannot influence what happens in this side. So the post-processing here can depend on the pre-processing here, and the post-processing here can depend on the pre-processing here, but this thing cannot depend on this one. So the rule is very clear. When I'm talking about contextuality, I don't have walls anymore. So that's the issue here. And for many things in contextuality, because it's not clear how to make things to mimic this wall in contextuality scenario. So what we came up with, the idea that solved the problem for us, or at least gave us a quite general class of operations that was useful, is this one. So now I will imagine that I have these two buttons in the same context. But instead of pressing them jointly, just for the sake of clarity here, I'll press them sequentially. So I'll see first what happens with the first one, and then what happens with the second one. But it's not necessary for you to understand it easily. Okay, so I press the first button. Just give me an output. With this output, I choose an input for the second box, and then I get an output. With this output, I decide an input for the third box, which in turn will give me an output. Okay? And now, if I do the same with the other button, I'll have another path corresponding to this button here. And when I see these lights here in the end, I can trace back the genealogy of these lights. So I know the path that led to this light turning on, and I know which was the path that led this light turning on. So what we need here is that what happens in this last box, the dependence of the pink buttons only depends on the path, on the pink path. And what happens with the purple buttons only depends on the purple path. So in order not to create contextuality with the dependence of this box on this box, I need that these probability factors like this. And of course, I can also take convex combinations of these things, but this gives the idea. So tracing back the genealogy makes the analogy of the wall to contextuality scenario. And if I come back to the Bell scenario, this genealogy tree would be exactly only on one side and only on the other side. So, okay. With this, we have a very general class of operations that transform boxes into boxes with an explicit and relatively friendly parametrization. So now we can actually make calculations with these things. And this was the open problem for those who were seeking for a research theory of contextuality, is that you had the objects, you had the quantifier, you had the applications, but you could not actually see if the quantifiers were monotonous under a good class of free operations. And this is what we provided here. So now the calculations follow more or less easily as we expected. So we can prove that a non-disturbing box, if you apply a non-contextual wiring to such a box, it will remain non-disturbing. So the non-disturbing set is preserved. And also what we wanted. We figured out that we had to define the operations in this way because we wanted this to happen. Contextual set is also preserved. Okay? And I will not enter in any of the details here, but if you're curious, you can ask me later. There were other some quantifiers already defined in the literature, so we could go to these quantifiers and check if they were monotonous under the operations that we define. So what is a quantifier? Here I'll use the notion that the contextuality quantifier is a function that takes any box into a real number, and this real number is meant to quantify how much contextual this box is. So I need this quantity to be 0 if the box is non-contextual, and it cannot increase under the action of a non-contextual wiring. So if I'm applying an operation that cannot increase contextuality, this quantity cannot increase. So it has to be monotonous under the non-contextual wirings. Okay, so useful contextuality quantifier is the relative entropy of contextuality, which is more or less a distance between boxes that is based on relative entropy. Okay, so we can prove that this is monotonous under non-contextual wirings. So another measure is the contextual fraction that is related to the convexity of these sets. It's also monotonous under the class of non-contextual wirings. But there was another measure, another quantifier defined more or less in the same fashion of this one. But this one, we can prove that it is not monotonous. So this is not a good quantifier if the entire class of non-contextual wiring is to be considered. Okay, so the calculations are straightforward, a little tedious. I would not all of this, but after we figure out how to define in the right way, then everything follows as we expected. So the difficult part was to figure out how we should define things. To be general, to have a large class of operations and still have all the things that we wanted. So, and recently we've been working with some other quantifiers, and the idea is just to replace relative entropy with geometric distance. So is basically here you have the set of non-disturbing boxes, here the set of non-contextual boxes. So our quantifiers are based in the geometric distance between the box and the set of non-contextual boxes. I'll also not enter in the details. You can see it here in this paper that is in archive for a long, long time, so we should do something with it. For the general case of contextuality, and for the special case of Bell non-locality with the trace distance, we have some really nice results with Rafael and Samurai that is there in the end. And the advantage of this is that it has all the nice properties that the quantifiers based on relative entropy have, but they are much easier to calculate, so to actually make these things more practical. Okay, so conclusions. The message I want you to take home today is that contextuality is not just a curiosity of foundations of theory, it has also some nice applications. And then it is important to study this feature from the point of view of resource theories. And our main contribution was the definition of this class of free operations, which we call non-contextual wirings. This was an open problem for a while. And relating to quantifiers, we were able to study monotones that were read in the literature to see if they were indeed good quantifiers or not. And we also proposed some new quantifiers based on geometric distance, which are easier to calculate than the ones that are based on relative entropy. Before I finish, I would like to make some advertisement. I don't know if I'm allowed, but we have this really, really nice conference in Florianopolis in November. And I would really happy to see you all there. There are some really nice people talking. And we have also a lot of discussions on, besides the scientific program, we have some other discussions that I think we have to have in our field and in academia in general, with also very nice people talking and very nice people organizing, and in a very nice place. And this is in the south of Brazil. It also has beautiful beaches. It's just a 48 hours drive from Natal. So I expect to see you all there in November as well. So thank you.